Right here, so here's the setup. I've got the generator here. I've got the leads out to the oscilloscope across a pair of legs. And what I do is I just try to turn this as steadily as I can. And then while I'm doing that, I just hit the single sweep. And then it comes up. For instance, here it's 5.43 hertz. 21.2 volts peak to peak, and 6.44 volts RMS. So I think it turns out the waveform is just a little bit off from sinusoidal, but it puts out some good voltage. I've got the leads to the oscilloscope across one pair of legs of the generator, and I'm going to turn the generator 3 turns. 1, 2, 3. We can see we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 peaks. So we get 3 cycles per revolution, or 6 cycles per revolution. So that will be helpful in determining converting frequency that we get here to RPM. Okay, another helpful piece of information is what the stator resistance is. So here I've got a voltmeter set to resistance, and we'll just measure across a pair of legs here. We get 64.5 ohms. And we'll measure across this one. Get 64.4 ohms. So or 64.5. So about the same. Okay, another question that comes up is what is the cogging torque on these things? There is a little bit, just not a lot, but there is some. And what I've done is I've taken this piece of PVC, taped it in place so it's approximately centered on the axle. The diameter is just under 6 5/8, so about 6.6. Something like that. Then I have a string wrapped around it, taped in place over this screwdriver, and I've got a little paper cup I can throw weights in, and I'm just going to put some weighty things in there until this thing decides to turn. So we'll see what sort of cogging torque there is in here. So put some bigger items in first. Put all these screws that I've got, put those in there, because I know it's going to take a little more than that. Okay. Start putting some washers in. Nothing yet. Add some more washers. I'm just going to keep going to smaller and smaller things, so hopefully it gets better resolution. Okay, I'm down to my smaller washers here. So let's see, put a couple in, some more in. There it goes. Alright, so this cup has all the weight in that it took to get the thing started. Now I'll just get a scale and I'll weigh this. So here's the cup with the hardware to get it going. This is just some extras. They didn't need those. So we'll turn on the scale. Just let it settle for a bit. Set this on. And it looks like it took 193 grams at that radius in order to get this thing started. So it just gives an idea of the cogging torque. Okay, from our generator test, we were looking at cogging torque. Remember we had the PVC pipe on there. It was about 6.6 inches in diameter. So the radius from the center to the edge where the string was is about half that, or 3.3 inches, about 0.084 meters. The mass that it took to start rotating was 193 grams, or 0.193 kilograms, The force that would apply, if you multiply by the acceleration due to gravity, 0.193 times 9.81, you get about 1.89 newtons. So the torque that it took to get the generator started would be this force times this radius, and we get about 0.16 newton meters, and that's what's required just to get things spinning. Alright, we looked at the generator. Just did a few test runs on the generator looking at the frequency and the peak-to-peak voltage and RMS voltage. I think I'm going to just look at, we saw that there's about 6 cycles per evolution. If you want to convert frequency then to RPM, get 1 revolution is 6 cycles, 60 seconds per minute, and it turns out it's simply RPM is 10 times whatever our frequency reading is. So that makes things pretty easy. So we can list RPM, and I'm looking at volts RMS because I think it's a little bit more consistent than the peak to peak, because I might not have been completely steady with the rotation there. So anyhow, we can plot VRMS versus RPM, and it turns out to be quite linear, and theoretically it's supposed to be exactly linear. So we can take the slope here, and I'll just pick this point out here. We've got an 8.47 divided by 70.7 RPMs, and we get 0.120 volts RMS per RPM. So that's the open circuit voltage across the lines. So that's line to line open circuit voltage. So we also learned that the stator resistance was, we measured 64 ohms, but when we measure line to line, that's measuring through 2 of the coils, so actually they're like 32 ohms each. Anyway, let's keep going here. We're going to try to estimate what the power output is of the generator at our rated speed, which was 303 RPM. So we can calculate our line-to-line open circuit voltage. 0.12 times 303 is 36.4 volts. And this is our model of our generator here. We've got the generator portion, and then I'm just using straight resistance. I'm not going to worry about inductance values and that sort of thing. So we had like 30 for each phase from neutral. We've got our generation portion, and then we've got 32 ohms. And then I'm applying an ideal load, which technically would be the complex conjugate of this, but since I'm only talking resistance, then it's just resistance here. And if we put it in a Y configuration here, this point is theoretically the same as that neutral point. So we don't have to run a wire over there. And so we'd have 32 ohms on each of those legs. So this is the voltage between the line to line, 36.4. If we want to find out what the voltage is just across one phase, we take that, divide by square root of 3, and we get 21 volts RMS. So if we want to find the current going through this resistor here, assuming this and this are the same value, we have the 21 volts RMS. The current goes through this resistor and this resistor, and we get 0.328 amps. So that would be the current, or 0.328 amps. Okay, so then the power delivered to this load here would be I squared R. So we've got our amperage, 0.328 amps squared, times the resistance 32, and we get 3.44 watts being absorbed by this resistor. But of course we've got 3 of them, so we multiply by 3. So our generator should be giving us about 10.3 watts into an ideal load. Now, if we're doing this into a battery, it's probably not going to be quite that efficient. You could maybe use the power factor to describe that efficiency, and I'm guessing it's around 0.6. So the power going to a battery would probably be about 60% of that, or about 6.2 watts. So as far as what I'm expecting out of this wind turbine, I'm expecting something in the neighborhood of about 6 watts if at rated speed.